You walk into a status meeting, drop a single number estimate on the table, and hope nobody asks too many questions. It looks solid on the schedule, but a single point estimate is a fragile promise. The moment it hits real-world pressure, that number falls apart. Look at the data here. A typical gut feel single point estimate carries a swing of plus or minus 40%. Typing that single duration into a project plan treats a guess as if it were a recorded measurement. This flowchart outlines a different approach. Instead of guessing a single number, you can triangulate a defensible range. It's called the range system, a 5-step method that routes multiple estimation techniques through a final expert check to find a calculated window of time. This system maps the practical boundaries of the work. When stakeholders see the realistic high and low ends of a task, they can make safe, informed decisions based on the actual distribution of risk. Step 1 is to reference historical data. Instead of trying to pull a duration from memory, you start by locating an analogous activity your team has actually completed in the past. On this project dashboard, we can see a past task, let's say build dashboard. We isolate its logged actual time of 20 hours. This becomes your objective base anchor. From there, we move to step 2, assess complexity drivers. You scale the historical anchor to match the new volume by extracting a unit rate, like 5 hours per widget. If your new requirement calls for 6 widgets, you apply that parametric math directly. 5 hours a widget multiplied by 6 widgets gives you a solid 30-hour base. Keep in mind, this specific technique requires reliable inputs. Parametric scaling only works if the tasks are highly repeatable and your historical dataset is clean. Rooting your estimate in scaled historical actuals helps eliminate memory bias. You are now working from a sterile mathematical foundation. Step 3 is to narrow with 3-point ranges. This step is specifically designed to quantify uncertainty. To do this, you need 3 distinct inputs from your estimator: an optimistic duration, a most likely duration, and a worst-case pessimistic duration. This formula on screen is the PERT calculation. It takes those 3 durations, weights the most likely scenario by multiplying it by 4, adds the extremes, and divides the whole thing by 6. Let's run our previous baseline through it. We take an optimistic 20 hours, our likely 30 hours, and a pessimistic 50 hours. Plug those into the equation and you get a weighted average of 31.6 hours. Applying this specific calculation forces estimators to confront worst-case scenarios, dragging hidden risks out into the open that a single likely number usually conceals. Step 4 is to gather bottom-up detail. This tree diagram shows the process in action. You take an ambiguous parent task, like building the dashboard, and break it down into its smallest measurable components. You estimate the effort for each individual piece, then sum them up for a more accurate total. There is a critical boundary rule here. Granular decomposition is time-consuming. You should only deploy this technique on critical path activities or deliverables with high visibility. When you have a complex deliverable, this is the only reliable way to isolate exactly where the heaviest effort is hiding. Step 5 is expert validate and calibrate. Math without human context is dangerous. Take your newly triangulated number to a subject matter expert. Their job is to sanity check that calculation against the real-world friction that formulas can't anticipate. Once the base is validated, you must add an explicit contingency reserve. This buffer is sized strictly according to the task's remaining risk profile. There is a major trap to avoid here. Contingency must never be hidden as invisible padding inside the base duration. It must be isolated and tracked separately. Looking at this calculation, you start with your validated base estimate of 30 to 34 hours. You add a distinct, explicit 10% contingency block. That process yields your final, defensible range of 33 to 38 hours. By layering mathematical triangulation with human reality checks and transparent reserves, you turn a theoretical calculation into a rock-solid operational commitment. This matrix shows the contrast clearly. You've moved away from the traditional model of relying on one person's gut feel. You now possess a probabilistic, triangulated range anchored to real data and reviewed by experts. There are 2 final operational rules. First, publish the entire range in all your schedule views, not just the midpoint. Second, when the project closes, log your actuals to feed your baseline for the next cycle. An exact single-point estimate creates an illusion of certainty. Real precision requires defining boundaries and rigorously testing them before they hit the schedule. Estimating is a systemic process, not an exercise in formatting a guess. When you follow the range system, you hold numbers that will survive any boardroom interrogation.